Well, so here we are taking a quick overview of chapter 6. So good news is, right, we cover 10 chapters in this class. So chapter 6 means we're past the halfway mark. So congratulations for getting there. So as we move into chapter 6, chapter 6 deals with three things that are very similar. It deals with trusses, it deals with frames, and it deals with machines. So trusses are a structural member that is usually made up of small pieces where we can neglect the weight, and those small pieces can carry a relatively heavy load. So if you want examples of trusses, if you climb up into the attic of your house and take a look at the roof structure, you will find trusses up there. You can look underneath the bridge and see a truss, although it's usually not quite as easy to see. They usually use boxes in that particular case as opposed to a standard truss. So good places to look at the roof, look at a house that's being constructed. A lot of times they use pre-fabricated trusses, so they're built in a factory someplace, and they set them up on the roof with a crane and stand them up and then build the roof structure on top of that. So these trusses are made up of members. These members are going to be in either tension or compression, right? As a mechanical engineer designing it, you would need to figure out how to size these members so that they can carry the load that they need to carry. Trusses are loaded at the joints. So there's going to be two methods that we're going to see here in a moment to figure out how to calculate the forces at those joints so that we can figure out what's happening inside of this truss. So this is a pain using their slides. So as I've already mentioned to you, I mentioned a few things already, right? So the trusses are made up of two force members. They're either going to be in tension or compression. So compression, they're being forced together. Tension, they're being pulled apart. Now, the reactions at the joints are opposite. So think about this. If you stood up and I grabbed your arms and started pulling your arms apart, right, that would be putting you into tension. However, your reaction force would be to try to pull your arms back away from the force that I'm putting on there. Right, the same thing would be true if I took and put you into a big bear hug, right? If I grabbed you and put you in a big bear hug, I would be putting you into compression. And again, your reaction force would be to push away to get the force away from you, to get the discomfort away. That's the reaction force that's happening. So loads are applied to joints. You can neglect the weight of the members because typically the weight of the member is very small, negligible compared to how much weight the thing can carry. They're joined together by smooth pins, right? In the case of a house, more than likely it's nails that are used to hold the thing together, and they're made out of wood in that case. So there are two different ways that we can do an analysis on a truss. And one of them is method of joints. It's the first part of chapter 6. And then the other is method of sections, which is the next part of chapter 6. So if you are given a problem where you are asked to find, well, first off, if you're asked to use the method of joints, then you know which one to use. But if you're given a problem where you're asked to calculate the force in every member of the truss, then that is a clear indication that you're going to use method of joints. If you are asked to find the force in some smaller subset of members in the force, then you use method of sections, which is the second part of it. So essentially method of joints is, this is a really simple, in this example of truss that's being shown, there's one simple triangle, right? So you can see there's a load applied to point B. There is a pin at point A and a rocker at point C. And I would assume, based upon what they're doing here for this example, that you were asked to find the force in all those. So you want to find the force in AB, BC, and AC. So essentially, method of joints is you pick a joint, and you need to pick a joint where you have less than, well, two or less unknowns, and you solve for the unknown forces. So in this particular example, right, they showed you point B, right? And we know the applied force of 500. We don't know the other two. So we would apply our equations of equilibrium. So think now chapter 3. This is point or particle equilibrium. So we got some of the forces in the x direction are equal to 0, some of the forces in the y direction equal to 0. We could write our two equations with our two unknowns and solve for FBA and FBC. Right, then the only thing that would be left would be the AC on the bottom, and you do either C or A, whichever one was easier, to find that missing piece. So I probably told you all these steps already, but let's just run through them here. So when you're doing method of joints, if the support reactions aren't given, what you need to do first is you need to apply your equations of equilibrium to find the support reactions. So in that first example, you notice there was a pin on one side and there was a rocker on the other side. So the pin has a X and Y reaction. The rocker has just a normal reaction. You have to find those first. You draw your free body diagram of your joint. Remember I said one or two unknowns. And you can assume the forces are all in tension, right? So if you assume they're in tension and you do the problem, applying your equations of equilibrium in step 3, and you get a negative answer, guess what? You know it was in compression and not tension. You apply your equations of equilibrium and solve for your unknowns. And continue to do that until all the forces are found. So that's how you do, and I'll do a problem in another video to show you how to do this. It takes a bit to do it. So the other thing that's important to recognize are zero force members. So the author uses these big words, these two non-collinear members. So essentially, if you can picture if you had either an L or a T, right? So when you apply your equations of equilibrium, if there is a force in the x direction going one way, you have to have a force in the x direction going the other way, right? Same is true for y and for z. If you had a 3D case, these are all going to be 3D. So if you look at point A, right, you see that AF goes completely in the y direction, and AB goes completely in the x direction. So since there is nothing on the other side to get rid of the x piece, and there's nothing on the other side to get rid of the y piece, AF and AB must be zero force members. Why? Because if they had any forces on those members, then you'd have to have something. They wouldn't be. The system wouldn't be in equilibrium, right? Remember, we're assuming that it's in equilibrium. The same thing happens with DC and DE. Again, you can always turn your axes. So if you put your x-axis on CD, right, you notice that CD is completely on the x-axis, and guess what? ED has an x component and a y component. Because it has that y component, those have to be zero force members, or the system wouldn't be in equilibrium. So when you identify zero force members, what you can do is you can take them off of your truss. So notice that the top picture has been simplified by removing A and D. Now, those are zero force members for the way the truss is currently loaded. There may be a condition that makes them not zero force members. Good example of this, if I mentioned before that I'm from Connecticut. So if you look at the trusses for the roof in Connecticut, there is a collar tie, and the whole purpose of the collar tie is actually to distribute the snow and ice loads that you can get on the roof. Rest of the time of the year, there is no force. It would be a zero force member during the summer, but during the winter, there's a force applied to it. So it's not there just for fun. There's probably some reason for it. Same thing is true here. Again, you could turn your axis and you could see, right, if we put the y-axis on AD, right, you'd see that, yes, we do. If we put the y-axis on AD, then our x-axis would be going on the BE plane there. Well, you have an x canceling out the other x, but you got no y to cancel out the AD. So boom, zero force member in that case. Since that one is a zero force member, we got the same situation at C, right? If we put our x-axis on that BE, you notice that there is an AC, and that AC has an x and a y component. The y component has nothing to offset it, so it must be a zero force member. Take them out, simplify it as shown in the bottom picture. So method of sections is, again, if you're given a problem and you said use method of sections, you're going to use method of sections. If you are given a problem where you're asked to not find everything but some subsection, so in this particular example, right, they want to find the forces in BC, GC, and GF. If you're asked that, you can do method of sections. Essentially, what method of sections allows you to do is cut the truss along a line that bisects the ones that you're looking for the force. Take those forces that you've cut and now represent them as a, right, it's a two force member, so we can represent that two force member as a force and we can solve the problem. So what do I mean? Glad you asked. Right, so if we look at that first problem, we cut it, good. We cut it along that line because we're looking for those three forces. We got two pieces, right? So we got a free body diagram now that has two pieces. We got a piece on the left, we got a piece on the right. Notice that the forces go in opposite directions. So they're actually both going out on BC, both going out on GC, both going in on GF. Again, you can reason through and figure out which is in tension and which is in compression. Don't waste your time. Just try everything in tension, do the problem, and guess what? Positive answers, it'll be tension. Negative answers, they'll be in compression. So we cut it. We get our two pieces. You then need to decide which side is going to be easier to work with. Hopefully, you see that the side on the left is easier in this case. Why? Because there's three unknowns on the side on the left. Right? The one on the right actually has 6 unknowns, and we could not solve that. Why? Because now we're moving into chapter 5, equilibrium for a solid body. So now we can add our moment equation. So we can get up to 3 unknowns because we now have the moment equation. We can't solve 6 unknowns, so we're going to work with the piece on the left in this particular case. Apply your equations of equilibrium, and voila, you can get your answer from that. So you draw a free body diagram. So they've already done that here. They drew both of them, right? You'd use the one on the left because it's the easier one for this. And what is it going to do? Oh, so yeah, you're going to, once you draw it, you apply your equations of equilibrium, knowing now that you're also going to have a moment equation available to you. So here's an actual example of doing that. So in this particular case, I'll run through this real quick. They want to find the force in KJ, KD, and CD. So you can see what they've done there is they've drawn that purple line. That's the point where you're going to cut it. Now, with moment of joints, you must find the support reactions. With moment of sections, you don't have to if they're not needed. Well, in this particular case, right, well, there's whatever side we take, whether we take the one on the right or we take the one on the left, we're going to need the support reactions. So the way you'd start this problem is you would solve for your support reactions at, well, you're going to need them at A because you're probably going to take that side over on the left-hand side. But you're going to find your support reactions. The support reactions at A, it's a pin, and the support reactions at G, A, roller in that particular case. And you cut it, you take your piece, and apply your equations of equilibrium to solve the problem. So first thing we do is hopefully, well, you can see here what they've done is they've added the support reactions, which I've already mentioned, right? We got a pin, so we got an AX and an AY, and we've got a roller, so we've got a GY, just a normal force on that side. So hopefully you recognize based upon the way this thing is loaded, right? AX happens to be 0 in this particular case. Why? Because there is nothing in the X direction. You're not really going to need the G side if you're going to use the left-hand side, and that's the one I probably would use in this case. So we can take a moment at point G, right, which will knock out the GY piece, and we can solve for AY, right? The 20K, the 30K, the 40 kilonewtons forces in the AY piece will all contribute to a moment at point G. We can solve for AY. Of course, once you got AY, right, you know all the forces coming down. You got, looks like 90 kilonewtons coming down, 56.7 is going up in AY, so the 90 minus the 56.7 is going to give you the GY if you really felt it. You needed that when you were done. So we got our piece, right? So we took the side on the left. We've got all the information that was given to us for the right triangle over there, the 2, 3 right triangle, the two sides that are given to us, and we're given FKJ, so we've got the three forces we're trying to solve for with the applied forces. Now, where we chopped it, of course, the 40 kilonewtons is gone. We needed that 40 kilonewtons to do the support reactions, but we don't need it for the rest of the problem. So typically, right, we got three equations. We can do a moment equation, some of the forces in the X, some of the forces in the Y. What you want to try to do usually first, and actually I've done these problems and I'll try to remember when I do some examples for this chapter to do one of these. You can do all moment equations and actually knock things out, right? Because moment equations will knock things out if the forces are going through the point. So the author starts this problem by finding the moment at point D. And you might say, hey, professor, point D is not on the picture anymore, right? Point D is off the picture. That's okay. But the reason why you want to use point D to solve this is you'll notice that, actually you could use K also, but the reason you want to use point D is because FCD and FKD both go right through point D, so they'll have no effect on the moment equation. So there you go, did the moment at point D, and we got a force for FKJ. It came out as a negative force. You see they drew it in tension, so a negative force tells us it is in compression. So now we know FKJ, so we can use that information to solve for the FCD and the FKD, right? So the way the author chose to do that is they chose to, and I actually might have done another moment equation, and again, I'll try to remember to show you a problem where I do that. But in this particular case, right, they sum the forces in the y direction, right? What do you have in the y direction? Well, KJ and CD, right, are both purely in the x direction. So we have the y piece of FKD, right? You could have actually started with this one, right? Because everything's known except for FKD. So you can use that equation to solve for FKD. All right, so now you got KJ, KD. So now you can sum the forces in the x direction and find FCD. And voila, those both came out as positive. You drew them in tension. They came out as positive. They are in tension. So the last part of chapter 6 deals with frames and machines. Frames and machines are a close cousin to trusses. They are structures. In this case, we've got a machine. No, actually, we got a frame. Sorry. In this case, they are close structures. They're mechanical structures. The difference being a truss is made up with all two force members. In a frame or a machine, we have at least one multi-force member. Right? Typically, frames don't move and machines do. So if you want a good example of a machine, think of a a pair of pliers. Right? If you had a pair of pliers, right, that is a typical machine. They move and there's forces that interact on the two of them. In this case, we've got a machine, and you can see hopefully that AC has multiple forces acting upon it. BD, on the other hand, is a two-force member. And just as I mentioned, right, frames typically are stationary and machines are moving. So the key for solving a problem for analyzing a frame or a machine is you need to draw a free body diagram, which hopefully you're doing that for everything by the time we get into chapter 6 here. However, you blow it apart. So in this case, right, we've got a simple frame. It would have been a truss if that 2,000 kilonewtons wasn't applied there. But with that 2,000 kilonewtons applied there, right, BC is now a multi-force member. So we blow it apart. So there's two pieces. There's the AB piece, there's the BC piece. We draw a free body diagram for each one of those pieces. So you notice, hopefully, if you didn't notice it the first time, right, FAB is a two-force member. So we can replace that two-force member with a single force, FAB, as shown there. Can't really do this problem because they didn't actually tell us what the angle or any measurements are so that we could figure out the angle, but you can figure out, right, there's the FAB. The other side, the C side, right, is got a pin, so there's a CX and a CY reaction on that end. Identify two force members, we talked about that. Identify pins, and there you go. So, right, the next step is, and this gets a little bit tricky, is you got to figure out where you can apply the equations to solve for the unknowns. What you want to try to do is look for a way to form an equation with one unknown. So what I would probably do in this particular case, again, we can't solve it because we don't have any measurements. But if you notice, if you took a moment at point C, right? If I took a moment at point C, both C forces would fall out of the equation, and I'd have the 2,000 newtons, and I'd have FAB. Both of those would contribute to the moment at point C, but the C wouldn't. I would be able to use that information to solve for FAB. Right? Once I had that, right, I could break FAB into its X and Y components. Right? The X piece of FAB would be equal and opposite to CX, and then the 2,000 newtons and the Y piece of FAB, right, the difference between those two, would give us the CY piece. So that's how you do that particular problem. So again, it can be, as I mentioned here, it can be challenging, and there can be a lot of unknowns. Right? If you have more, if you blow apart a frame or a machine and you find that you have more than 3 unknowns, guess what? You cannot start with that piece. You need to start with another piece of the frame, solve for that, and then bring back that unknown so that you can solve for the other one. So there you go. There is an overview of Chapter 6.